Hi, I'm Ryan, and welcome back to SparkFun Electronics. Today we're going to be covering some of the physics concepts behind many of the basic circuits that we've looked at in the past. A quick reminder that if you enjoy our content and want to see more with topics ranging from explaining circuit concepts to exploring Arduinos, please subscribe to our YouTube channel. It's completely free and you can unsubscribe at any time. Before we can get into discussing what exactly is electricity, we first have to discuss something called electric charge. Electric charge is a property of matter, just like mass or volume. So all pieces of matter have some electric charge that describes it. This charge is measured in a unit called coulombs. Now, if we look into the structure of an atom, which is the basic building block of all matter, we will find some particles of electric charge. We have protons, neutrons, and electrons. Neutrons have no electric charge, protons have a positive electric charge, and electrons have a negative electric charge. So now we can discuss what exactly is electricity. Electricity is the movement of electric charges. If we look at an atom, protons are stuck in the nucleus, so they can't move easily, and so they can't make up electricity because they can't move, they're fixed in place. However, electrons are just orbiting around the nucleus freely and can move easily, so these electrons are actually what's flowing from one atom to the next, making up electricity. So whenever you have a wire that has electricity flowing through it, the atoms in the wire are actually passing electrons from one to another. So now that we have a general idea of what electricity is, we're going to move into some more concepts of describing that electricity. First, we have voltage. Voltage is the measure of difference in electric potential between 2 points. This is a pretty complicated definition, but you can think of it as a measure of how hard the electrons are being pushed in a circuit between 2 points in that circuit. So voltage is measured in volts and has another name, which is EMF, or electromotive force. Now, we're going to cover what exactly a battery is. A battery is something known as a voltage source, meaning that it provides voltage. A battery has a positive and negative terminal, which are the pointy and flat end on a battery respectively. So what a battery does is provide a difference in voltage between the positive and negative terminal, which means that when the two ends are connected in a circuit, the electrons in that circuit are being pushed from the negative end of the battery to the positive end. This creates a flow of electricity inside of our circuit. So we can demonstrate that in this diagram. To explain the diagram a bit, the set of lines on the left side with the 9V next to it represents our voltage source, or our battery. Next, we have the line which connects the positive end of our battery to the negative end, and this represents our wire. So as explained before, the voltage difference between the positive and negative terminal of our battery actually causes electrons to be pushed from the negative terminal of our battery through the wire to the positive terminal. However, electrons have a negative charge, and we typically like to think of electricity as flowing in the positive direction. So when we talk about the flow of electricity, we typically make it go from the positive to the negative end, even though electrons go the opposite way. This flow of electricity can be measured by something called current, which measures the speed of electric charges as they move through the circuit. This is measured in a unit called amperes, or amps for short. A higher current means electricity has a higher speed, while lower current means electricity has a lower speed. It is very important in our circuit that they have to be complete loops. This is so that we can use the potential difference between the positive and negative terminal of our battery. You can also think of it as if there were no complete loop, the electrons at the end of the wire would have nowhere to go since there would just be a dead end at the end of the wire. The next concept we'll be covering is resistance, or the opposition to the flow of electricity. We discussed voltage, which measures how hard electric charges are being pushed in a circuit, and current, which measures the speed of electrons as they're being pushed. If you apply the same voltage to materials of different resistances, the one with the higher resistance will have a lower current than the ones with a lower resistance. This is because the materials with the lower resistance won't oppose the pushing of the voltage as much, allowing the electric charges to move faster. And this resistance is measured in a unit called ohms. Every component we use in our circuit, such as light bulbs, buzzers, and motors, will have some resistance to them. Even wires technically have resistance, but it is very small. There are also some components called resistors that serve no purpose other than to provide specific resistance value in a circuit. While this may not seem initially useful, they actually are incredibly useful, and we will see why at a future time. Here, we have another circuit diagram with a voltage source and a resistor. The object on the right is a resistor, and note that we use a different symbol on the left to denote our voltage source. The two shown so far are both common symbols, but we will mostly be sticking with the one on this diagram from now on. What happens in this diagram is that the voltage source will push an electric charges in the wire with a value of 6 volts. However, this 200 ohm resistor will resist this flow. This means electric charges will flow slower than if there were a smaller resistor or no resistor at all. So now we can introduce Ohm's law, which gives us a way of directly relating the voltage, current, and resistance going through a component. The equation is voltage equals current times resistance. If we know two of these, we can solve for the other one. So here we have a diagram from earlier where we were given the voltage source of 6 volts and a resistor of 200 ohms. We want to find the current going through the resistor, and we can find this by using Ohm's law. We know that the voltage source is providing us with 6 volts for the entire circuit, and all of this is going through the resistor since the only thing in our circuit. The resistor has a value of 200 ohms, so this means that current equals voltage divided by resistance, giving us a value of 6 divided by 200 equals 0.03 amps. The final concept we're going to go over for today is power. Power is the measure of the energy used by a component over time, and is measured in a unit called watts. We can calculate the power consumed by a component using the power law, which tells us that power equals current times voltage. So here we can use the power law to find the power being consumed by the 200 ohm resistor. We found before that the current going through our resistor was 0.03 amps, and the voltage going across the resistor was 6 volts. This gives us a power of 0.03 times 6 equals 0.18 watts. Now we're going to talk about some electrical components that we have used in the past. As said before, all these components have resistance value associated with them, and so they can be modeled in our circuit as a resistor. The different values that we've calculated, such as the current, voltage, and power of a resistor, can be translated into properties of these components. For instance, LEDs, or light-emitting diodes, have a brightness depending on the power consumed by the LED. Passive buzzers have a volume depending on the voltage across them. For motors, the voltage determines the speed of the motor, and the current determines the torque or rotational force of the motor. In a future video, we will show you real-world examples that demonstrate these characteristics. Here we have two LEDs. One will have a resistance of 25 ohms, and the other will have a resistance of 50 ohms. They will both be attached to a 3-volt battery. We can model this with the circuit diagrams shown, where we have a voltage source attached to a resistor of the respective resistance. We can then calculate the power consumed by both of these resistors to find out which LED will glow brighter. Remember that from before, the power consumed by the resistor is directly related to the brightness of the LED. The one on the left will have a power consumption of 0.18 watts, while the one on the right will be 0.36 watts. Since LED number 2 has the higher power consumption, it will glow brighter. The final concept we're going to talk about for today is something called short circuiting, which is what happens when you have a voltage source attached to a very low resistance. One example when we'd have this is if we had a circuit with just a wire, which has a very low resistance as we discussed before. We can do some calculations and find that the power consumed by the wire with very low resistance would actually be extremely high, and this power would turn into heat energy, causing the wire to catch on fire. This can be seen in the image on the bottom right of the screen, which shows a gum wrapper being used to connect the ends of a battery and consequently bursting into flames. Here, the gum wrapper acts as our wire. This is why it's super important to be very careful while working with circuits, because if you accidentally short circuit something, you could severely injure yourself or damage your surroundings. So that's all for today, and I really hope you learned something new. Our next video will be about more advanced circuits with multiple resistors and showing how to solve for the voltage and current going through each of them. If you like this video and would like to watch similar content, I would appreciate if you would like this video and subscribe to the SparkFun Electronics YouTube channel. You can also click the notification bell to get updates whenever we post a new video. Until then, stay creative and have a great day.